Okay, we will continue our discussion on Fourier series. So, in particular, we will start now looking at discrete time Fourier series. Okay, so what we have seen so far is for the continuous time signals. So, now we will see how periodic discrete time signals can be represented by the discrete time Fourier series. So, as you know, in the discrete case, x of n is called periodic with the period capital N if x of n is equal to x of n plus n, and the smallest such capital N is the fundamental period. And if n is the fundamental period, the fundamental frequency in radians per sample is given as omega naught is equal to 2 pi by n. Okay. Now, for the there are several important differences between continuous time signals and discrete time signals, periodic signals. We have seen that in the when we studied about those signals in the first few lectures when classes were present, and also when we started learning about the Fourier series, the continuous time Fourier series, we talked about harmonically related complex exponentials. So, in the similar case for the discrete time case as well, we have the harmonically related discrete time harmonically related complex exponentials, which look like this, which is a set phi k, which looks like e raised to j k omega naught n, right, where k takes on various multiples, values like this 0 plus or minus 1 plus or minus 2, so that every element in this set is obtained by giving integer values to k, and these elements in the set are all the fundamental frequencies of each of these elements in this set are multiples of the fundamental frequency e raised to j of the complex exponential e raised to j omega naught n, right, where omega naught n forms the base signal which has the fundamental period, and all the signals in this set are all periodic with the period n, the period of the fundamental. Okay, the fundamental period will be a fraction of capital N, just like how we saw in the continuous time. But all these discrete time complex exponentials, harmonically related complex exponentials, are also all periodic with period capital N, which is the period of the basic e raised to j omega naught n, where k is equal to 1. Okay, so the important difference is that in the continuous time case, there were an infinite number of harmonically related complex exponentials. Okay, so for a particular value of k, you will get e raised to j some k omega naught n. K can be 10, 20, 30, 50, 1 million, whatever. So for every value of k, you will get a different harmonically related complex exponential. But in the discrete time case, there are only n distinct signals in this set. So that means there are only n distinct harmonically related complex exponentials. There are only n of them. N where n is the same as the n of the fundamental period. Why is this? This is because if you remember, we saw that discrete time complex exponentials which differ by an integer multiple of 2 pi are identical. You cannot distinguish them. So, each complex exponential which differ by 2 pi in their frequency are the same. There is no difference. Okay, so that means if you look at the set of harmonically related discrete complex exponentials, you will get phi 0, phi 1, phi 2, phi 3, phi 4 up to phi n minus 1, because those form the n distinct signals in that set, after which it begins to repeat. So that means phi 0 is equal to phi n, and phi 1 is equal to phi n plus 1, and so on. Now this is just like how you have the circular indexes in Python arrays, right? Something similar to that. So this is the main difference from the continuous time complex exponentials. So as a result of this, the Fourier series representation of discrete time periodic signals are a finite series. Whereas in the continuous time case, we had an infinite series. In the discrete time case, the Fourier series is a finite series. And the series periodic signal x of n is represented in terms of discrete time Fourier series in this manner: ak e raised to j k omega naught n, where k takes on a range of n successive integers. So this is not an infinite sum. Please keep this in mind. So going by it, there are a lot of parallels between the continuous time case Fourier series and the discrete time Fourier series. So here are the synthesis and analysis equations. They are basically the same, except that now it is a the summation here is going to be a finite summation, and of course it is a discrete signal. The form of the analysis and synthesis equations remain the same. And now the important difference is here. What can you say about the A case, right? So A case are the coefficients for e raised to k. E raised to, I mean, like AK is the coefficient for the complex exponential e raised to j k omega naught by n. Okay. So because the frequencies omega naught and omega naught plus 2 pi for any multiple of that 2 pi, that is omega naught is equal to omega naught plus k 2 pi. As you vary k, you get the same signal, there is no difference. The AK values will repeat periodically with period n. So that means the Fourier series coefficients are also periodic for the discrete time case. We will see an example. For example, in this is example 3.10 in the book. It is we had done a similar example for the continuous time case. So we have to represent the periodic, the discrete time periodic signal sine omega naught n in terms of its Fourier series. Now sine omega naught n is of course a discrete time sinusoid, and we saw that there are certain conditions for this sine omega naught n to be periodic. Not all discrete time sinusoids are periodic. For discrete time sinusoids to be periodic, there was a condition which the frequencies have to obey. The condition, if you remember again from chapter 1, was that omega naught must be an integer multiple of, or it must be a fractional multiple of 2 pi. Omega naught is of the form is 2 pi m by n, okay, where m and n are integers. So x of n is periodic only if 2 pi by omega naught is a integer, and in this case omega naught will be 2 pi by n, and hence if this is the case, if your omega naught can be written in this form 2 pi by n, then x of n has a fundamental period of n. So I said that the omega naught must be a fractional multiple of 2 pi. Omega naught is equal to, so this omega naught is actually equal to 2 pi by m by n. Okay, so here in this case the only difference is that here your m is equal to 1. Okay, this should be the condition for a discrete time sinusoid to be periodic. So in this case the fundamental period will be n, and we can expand this using the Euler's formula, and you will get the two coefficients, so e raised to 2 pi e raised to j 2 pi by n and e raised to minus j 2 pi by n. So these are the AK values for k is equal to 1. So 1 by 2j and minus 1 by 2j form the Fourier series coefficients in this case. Okay, so this can be obtained by inspection. By looking at this and comparing it with the form of the Fourier series, you will get the values of the AK, and that is plotted here in this case. And this is actually a complex number. So this is actually 1 by 2j. So actually to plot it, you need to plot it in two plots. You need to plot the magnitude and the angle, but here they have just shown the complex number as the plot. Okay. So this is for n is equal to 5. This is so you can see that the AK coefficients here is 0. So the AK coefficients, okay, so there is A1 is 1 by 2j, A minus 1 is minus 1 by 2j. So you can see that after, so these two keep repeating. See here, this is a consequence of the AKs being periodic, because of the fact that e raised to j omega naught k, e raised to j omega naught n is same as e raised to j omega naught plus 2 pi n, okay, because complex exponentials separated by a multiple of 2 pi in frequency are indistinguishable. So this is for n is equal to 5, and you can see that this is the same period is maintained here. So this is ak, this is a1 here. So 1 plus 5, 6 will also have the same thing. 6 plus 5, 11 will also have the same value. So this is the one which repeats here, and this is the one that repeats here. Now in the other case, if we also have, for example, if your omega naught is 2 pi m by n, then of course m and n here have no common factors, they are relatively prime. Okay, so if you write it like this, again if the sinusoid has this fundamental frequency, again you can write it in terms of Euler's formula, and it is the only difference is that now instead of m being 1, this is now some m. So that is what is shown here for sine 3 2 pi by 5 n. Okay, so here 3 and 5 are relatively prime. The omega naught is equal to 2 pi 3 by 5, 2 pi 2 pi into 3 by 5. Okay, so here also the period is going to be 5. You can refer to chapter 1 if you want to brush that up. The period is going to be 5. It's just that this sinusoid takes 3 cycles to repeat, because that is how the periodicity comes after 3 cycles. So so you can see that here also when you expand it, it is just that 3 and k is equal to 3 and k is equal to minus 3 are the two Fourier series coefficients, and that is what is shown in the plot here. At 3 there is a peak 1 by 2j, and at minus 3 also there is a peak minus 1 by 2j. Okay, so this is one and this is the second one. So these are the two coefficients. So you can see that this also are periodic with a period of 5, because this is the fundamental period here. So 1 2 3 4 5. So after 3 there is one peak at 8 having the same value of 1 by 2j. Again, this is a complex plot. They have shown the complex number in a single plot. So please go through the example, you will understand it. Now we will see one more illustrative example. This is example 3.12 from the book. So if you remember, in the continuous time case, we had looked at the Fourier series expansion for a symmetric square wave. So this is the discrete time counterpart of it. So there is a square wave which has a period n. So this is 0 here and this is n. So this is centered around 0. So from n1 on either side of 0, there is takes the value 1. After that it goes off to 0 until it reaches the next cycle. So here also the since this is symmetric wave, the next at n also there are a small part of the wave is on the left side of n as well as on the right side of n, and so on. That also has a value of 1. So this is the symmetric square wave. Okay, so the n1 is the fraction or is the amount of samples which is 1 in the total period of n. Okay, out of the capital N, only n1 samples are 1, all the others are 0. So if you want to compute the Fourier series of this, we apply the analysis formula as just we did in the continuous time case. You expand this, you put this, and you do some change of variable here, so that the summation can be made into m equal to 0 to 2 n1, because only n1 values are non-zero, all the other values are 0. We need to do this summation over only one period. So if you work out the expression, you will see that ak is equal to 1 by n over this term for k not equal to 0, not plus not equal to 0, not equal to n, not equal to 2n, and ak is equal to 2n by n1 plus 1 by n for k is equal to these values 0 plus or minus n plus or minus 2n and so on. So if you plot them, so you can see that these are real expressions. Okay, this is the real value, this is also a real value. So this plot is from the textbook. It shows the Fourier series coefficients for various values of n1 and n. Okay, so n1 here is 5 and n value is kept on changing, just like how we did in the continuous time case. So basically, as you can see, when n is 10, and n1 is 5. So this means half of the period is occupied by 1, the other half is 0. This is n1 is 5 and n is 20. So that means 1/4 of the period is 1 and the remaining values are all 0. And this is even bigger. That means only a very small fraction of the period is occupied by ones, most of the period is 0. So essentially this means it is a very narrow pulse. The square wave is very narrow like this, whereas this one, the square wave is a bit more broad. Okay. So we saw the same kind of behavior. Of course here the spectrum repeats, right, because this is a discrete time Fourier series, and so after every period of n it will repeat. So that is why we have a periodic signal here in the spectrum. These are real values, mind you. So the main thing is, as the square wave expands in time, we saw that it becomes more compressed in frequency. And similarly, as this becomes more narrower in time, this is the time domain, as it becomes more narrower here, it becomes broadens out in frequency. So this is the same behavior which we saw also for the continuous time case. So this is an important interplay between time and frequency resolution. We will learn about it later, and just keep this as an observation for the moment. Other issues which we saw there, like Gibbs phenomenon, where at the point of discontinuity, a continuous time signal, when we represent it with the Fourier series, had a small offshoot at the points of discontinuity. So because here we are dealing with finite sums, Gibbs phenomenon does not exist for discrete time Fourier series, and if the number of partial sums taken in the Fourier expansion is equal to n, then exactly the Fourier series will exactly represent the discrete time periodic signal. X hat of n becomes equal to x of n. Now properties of the DTFS pretty much carry forward to the same thing from the continuous time series. We will not go into the details. All the properties are listed out in table 3.2. Please have a look at that. Just an important difference is that of the multiplication property. This is again a matter of notation. So xn transforms to ak, that is xn has the Fourier series coefficients ak, yn has the Fourier series coefficient bk. Both of them are periodic with period n, capital N. Then if you multiply them in time, xn multiplied by yn, where you have pointwise multiplication, and take the Fourier series of that, you will see that again, similar to the continuous time case, you get a convolution. So essentially multiplying in time is equal to convolving in frequency. Multiplying the time domain samples is equivalent to convolving their Fourier series coefficients. But except here is that here the convolution is not an infinite sum. The convolution here is a finite sum because of the periodicity property. We just need to do the convolution over one period. So this is a periodic convolution. So just to recap, I mean just an important difference, just to highlight the difference. So again, this is the square wave example. This is the continuous time periodic square wave, and it has a Fourier spectrum like this. And this is the discrete time periodic square wave, and it has a spectrum like this. So so the important thing to remember here is, see, the fraction of how much this is the period. Okay, it's from 0 to t. This is the period. Now this t1 here represents the fraction of the period where the sum is non-zero, where the square wave, where the signal is non-zero. So as it becomes, so this is a pulse, and as more and more of the period gets occupied by 1, the pulse, the square wave becomes broader and broader, and as it becomes broader, it becomes narrower. The spectrum of the square wave becomes narrower. This was the behavior which we saw. So the same behavior is there in the discrete time case also, which we just explained in that example. Narrower the spectrum, narrower it is in time. So the broader it is in time, narrower it is in frequency, and the narrower it is in time, broader it is in frequency. So the important difference here I want to highlight when you look at the two spectra here is that, of course, this is the discrete time spectra because it is periodic. Discrete time spectra, the Fourier series coefficients repeat, whereas in the continuous time they don't repeat. So please keep this difference in your mind.